Amplifiers are built to operate within a specific, stable range called the midband. Within this frequency range, the voltage gain remains nearly constant, allowing a signal to be magnified evenly. If an input signal drifts outside this midband, different frequency components of that signal are amplified by different amounts. The waveform loses its original shape and emerges completely distorted. The physical limitation causing this distortion stems from a single component common to almost every amplifier design, the capacitor. The impedance of a capacitor, represented by the formula Z sub C equals 1 over J omega C, is inversely proportional to frequency. When the frequency drops towards zero, the impedance approaches infinity. The capacitor acts like a brick wall, blocking the signal entirely. Capacitors act as natural gatekeepers in any circuit. Their physical properties define the exact upper and lower boundaries of an amplifier's functional bandwidth. This frequency response curve maps those exact boundaries. The green shaded region is our stable midband. System bandwidth is the difference between the high-frequency corner, FH, and the low-frequency corner, FL. Notice they sit exactly where voltage gain drops 3 decibels below its midband maximum. The decibel scale is logarithmic. Plugging a -3 decibel drop into the equation reveals a voltage ratio of 0.7071. This means the corner frequencies mark the exact point where the system's gain has reduced to roughly 70.7% of its peak power. The low-frequency drop-off at FL is straightforward to trace physically. The discrete coupling and bypass capacitors placed intentionally in the circuit begin to act as open circuits as the signal slows down. The high-frequency drop-off is not caused by specific, visible components on a breadboard. It is a systemic issue caused by parasitic interactions within the active device itself, which requires a mathematical model to calculate. At high frequencies, internal parasitic capacitances between device terminals short the signal. The most severe impact comes from something known as the Miller effect. On this amplifier block, note feedback capacitance C sub F. Applying Kirchhoff's law, we sum the input currents. By substituting output voltage with internal gain times input voltage and grouping terms, we get the Miller input capacitance, feedback capacitance multiplied by 1 minus the gain. Since this is an inverting amplifier, the gain is negative. The math proves a severe consequence. The Miller effect takes a tiny parasitic feedback capacitance and multiplies it by the amplifier's total gain, creating a massive virtual capacitor that chokes high-frequency signals. This slide shows the formula for Miller output capacitance. When applied to an amplifier with a voltage gain significantly greater than 1, the internal fraction approaches 0. Consequently, the effective Miller output capacitance simplifies to roughly the physical feedback capacitance itself. The complete mental model relies on 2 specific mechanisms. Macroscopic, physical coupling capacitors dictate the low-frequency limit, while microscopic parasitic capacitors, multiplied by the Miller effect, dictate the high-frequency limit. Mastering how to calculate and manage these boundaries allows you to design circuits that hit the target midband without clipping the signal. Now, apply these formulas to the next problem set involving a common source FET amplifier.